Hello and welcome to online lecture number 4 for Chemistry 112 for the spring semester of 2020. In today's lesson, we're going to talk about entropy. And entropy, as we learned in the previous lesson, is a measure of the dispersal of matter. What we mean by that is that a state of higher entropy is a state with higher dispersal of matter. And also what we learned from the last lecture is that a positive change in entropy, a delta S of greater than 0, is favorable for spontaneity. So it's a condition that tends to make the process spontaneous. What we hope to learn in this lesson is how entropy is related to probability. And the reason why a delta S that's greater than 0 is favorable for spontaneity is because it's more probable than an ordered one. A state of particles which is more disordered, more random, is more likely, more probable than an ordered one. We can equate entropy and probability by an equation that Boltzmann first proposed about 100 years ago, which says that the entropy of a particular state is equal to a constant times the natural log of W, where W is the number of ways or microstates that particular state can be achieved. And we can calculate S if we can calculate W, and we can calculate W because W is equal to, for a system composed of n particles distributed among n boxes, so capital N particles distributed among lowercase n boxes, W is equal to the number of boxes, lowercase n, raised to capital N number of particles. So a couple examples of applying this equation. If we have a simple example where we have 3 coins, let's say 3/4, in a box, and they're all initially all heads up. We close the lid of the box, we shake it, and what we find is that when we then open the lid of the box, there are 8 possible outcomes, 8 possible microstates, because W is equal to the number of possible boxes, so either the coin will be tails up or heads up at the end, raised to the number of coins, which is 3, so 2 to the third is equal to 8. So there are 8 possible outcomes. The ordered outcome, the ordered microstate, would be heads, 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 because we start off with all heads, so an ordered outcome would end up with all heads. This can happen, but because of the 8 possible microstates, only one of those is this perfectly ordered microstate. We only have about a 1 out of 8 chance of that happening, or 12.5% chance. A disordered microstate, so something other than this ordered microstate, such as heads, heads, tails, or heads, tails, heads, that's much more likely to happen. About 7 out of 8 attempts, we'd expect to get a disordered microstate, or 87.5% chance of it happening. So an ordered microstate is ordered, it's less random, it has lower entropy compared to a disordered microstate, which is more random and therefore has higher entropy. And as we've seen in this very simple example, the disordered microstate, the one with higher entropy, is more likely to happen because it has higher entropy. Likewise, the ordered microstate is less likely to happen, less probable, because it has lower entropy. Another more general example is that if we distribute capital N number of particles, 4 particles, among lowercase number n 2 boxes, then this equation allows us to predict that we expect to have 16 microstates, 16 possible outcomes. And if we list all 16 possible outcomes, then what we'll notice is that some of these outcomes are identical to one another, such as this outcome set of outcomes B, where each of these 4 microstates are identical and that they all have 3 particles in the left box and 1 particle in the right box. 3 particles in the left box, 1 particle in the right box, etc. We call these identical microstates distributions. So in other words, with these 16 microstates, there are 5 possible distributions. We'll call them distribution A, B, C, D, and E. So of these 16 microstates, notice that there's not an even number of microstates per distribution. In fact, there is one distribution, distribution C, that has the highest number of microstates. 6 of those 16 microstates are in distribution C. So in other words, when this arrangement of distributing 4 particles among 2 boxes, distribution C is the most likely to occur. And the reason why it's the most likely to occur, then there's also distribution C is the one with highest dispersal of matter, because the particles are evenly distributed between the box on the left and the box on the right. And because it has the highest dispersal of matter, the most probable one is also the one with the highest entropy. Conversely, also notice that the least possible distribution, distribution A or distribution E, also is the one with the lowest entropy. Because notice, in other words, the least dispersal of matter. Because in these distributions, all the particles are constrained to just one box. So once again, the higher entropy is more probable, lower entropy is less probable. The take-home message from all this discussion about these two equations really has to do with this, and that the number of microstates and the entropy, as the number of microstates increases, that increases the entropy because of this relationship, and the number of microstates will increase as the number of particles increase and or as the amount of space to place those particles increases. So, in relevance to chemical applications, when we have a physical chemical change, the direction of the change that we predict to have a positive delta S, the direction we predict to be favorable for spontaneity, will be the one that either leads to an increase in the number of particles and or an increase in the volume of space for those particles to be placed in. So if you apply these ideas to a couple examples, first look at the entropy of gases. So for the expansion or contraction of an ideal gas, and we saw this picture in the previous lecture, and the idea is that we have all the gas constrained within flask A, a vacuum in gas B, we open the stopcock, and now we have a more or less even distribution of gas particles in flask A and flask B. This direction is spontaneous because notice that in this direction, going from a state of lower entropy, lower volume, smaller number of boxes, so to speak, to put those particles in, to a state of higher entropy, higher volume, a higher number of boxes. Whereas the reverse is non-spontaneous because we're going from a state of higher entropy to a state of lower entropy. As we talked about in the previous lecture, it's non-spontaneous does not mean it can't happen. It just means it can only happen with ongoing outside intervention. It's not, in other words, it's not going to happen on its own. For this particular process, we can not only predict the sign of delta S, but also even calculate delta S, because delta S is equal to N times R, where N is the number of moles of gas, R is your gas law constant, times the natural log of this ratio, the ratio of the final volume to the initial volume. So we can see that in a expansion process, so left or right in this picture, the final volume is greater than the initial volume, which means this ratio is greater than 1. Natural log of a number greater than 1 is positive, which then will give us a positive delta S, as we'd expect, lower entropy to higher entropy, positive change. Whereas the reverse, in the contraction of a gas, go from this picture to this picture, it is non-spontaneous. It does give us a negative delta S because in a contraction, the final volume is smaller than the initial volume. So this number is less, this ratio rather is less than 1. Natural log of a number less than 1 is negative, so therefore it gives us a negative delta S. Likewise, we could also calculate delta S not with knowing the volumes, but rather knowing the pressures. In a expansion, because the volume is increasing, the pressure is going to decrease. So we can use this equation. And likewise, if the final pressure is greater than the initial pressure, then this ratio is less than 1, which would then give us a negative delta S. Entropy is a state function, like most other thermodynamic properties. And it's because of that, we can calculate delta S for a particular process, particular physical change or chemical change, only by knowing the entropy we end up with and compare that to entropy we start with. So for our chemical reactions or physical changes, this will be the entropy of the products compared to the entropy of the reactants. So for physical state changes, kind of the simpler type of change, we have all we need to worry about is how does the entropy of a solid compare to that of a liquid, compare to that of a gas. And comparing our models, notice that in a solid phase, the particles are very tightly packed. and there's very small number of microstates, and so therefore relatively low entropy for a solid phase, less randomness of the distribution of those particles, compared to certainly the gaseous phase, where the particles are very randomly placed, high dispersal of matter. And then the liquid phase is somewhere in the middle. So generally speaking, we'd say that the entropy of a solid is less than that of a liquid, which is less than of a gas. So consequently, in a physical state change, such as the vaporization process, going from a liquid state to a gaseous state, we're going from a state of moderate entropy to a state of higher entropy. There's a net increase in the amount of entropy, liquid phase to gaseous phase. So therefore, this process is associated with or has a positive delta S. Conversely, the reverse, the condensation process, go from a higher state of entropy to a lower state of entropy. So therefore, delta S is negative. With chemical change, for example, this one where we're converting 1 mole of N2O4 molecules into 2 moles of NO2 molecules, notice that in this process, we're going from a smaller number of particles to a larger number of particles. Because there are more particles on the product side, the number of microstates will be much larger, so therefore the entropy will be much larger. So we're going from a state of lower entropy to a state of higher entropy. So the forward reaction would have a positive delta S, and likewise in the reverse reaction, higher entropy to lower entropy would have a negative delta S sign. And then the dissolving of something like sodium chloride, going from a solid state, low entropy, less randomness, to the aqueous state, higher entropy, because we have more randomness, a greater distribution, greater dispersal of matter in this picture compared to this picture. So the dissolving of most solid substances into their aqueous forms gives us a positive change delta S. Likewise, the reverse, the precipitation event, will give us generally a negative delta S. And then finally, to finish up with a couple of examples that normally, if we were meeting class, I would give you a few minutes to work on this on your own, then we go over the answers. You can still kind of replicate that by, if you want to pause the video now and then kind of do these on your own, predict simply for each of these 3 different, or 5 different rather, physical or chemical changes, do we expect to have a positive change or negative change in the entropy? So for the water vapor condensing, we're going from, as we just mentioned a few slides ago, going from the gaseous phase to liquid phase, a state of higher entropy to a state of lower entropy. So therefore, that's a negative delta S less than 0. For the separation of oil and vinegar salad dressing, going from a more random distribution of the oil and vinegar molecules to now when they separate, they're going back to a more ordered arrangement. So a lowering of the dispersal of matter. So that also will give us a negative delta S. For the dissolving of solid sugar in tea, we're going from a solid state of sugar to the aqueous form of sugar that tends to increase the dispersal of matter. So therefore a positive delta S. And these last 2 chemical changes, going from 2 moles of a solid substance to 2 moles of a solid substance and 1 mole of a gas. So not only are we increasing the number of particles on the product side relative to the reactant side, but also, and more importantly, one of the products rather is a gas. So generally speaking, anytime that in a process it leads to an increase in the number of moles of gas, because gas has such high entropy, that's going to tend to allow us to predict accurately that the process will have a positive delta S. And then finally, this precipitation process, where go from 2 aqueous ions to the solid form of substance. Aqueous form of substances usually have higher entropy compared to a solid, so higher entropy down to a lower entropy means it's going to have a negative delta S. So hopefully you have a better idea as to what entropy is and how that's related to randomness or dispersal of matter. In the next lesson, we're going to see then directly see how entropy plays a role in determining whether or not a process is spontaneous. Because notice we'll see have some examples, even this very common example, the separation of oil and vinegar. We know this process is spontaneous, it's going to happen on its own, even though it has an unfavorable delta S value, even though it has a negative delta S value. So there must be something else involved which helps us predict whether it's going to be spontaneous or not.